Hello, this is a course called Algorithms 2, and in this course we will introduce algorithms in many domains, including the algorithms in graphs, in geometry, in strings on symbols, in linear programming, in numbers, polynomials, matrices, and so on. In this course, we assume certain background that includes some knowledge of elementary data structures, such as queues, stacks, binary search trees, heaps, etc. In addition, we expect that you are familiar with analysis of very simple algorithms, such as sorting algorithms. You are familiar with hence you are familiar with big O notation, small o, omega, theta. Okay. So, today we will start with a very elementary algorithm in graph theory, which probably you are familiar with. The algorithm is to determine the shortest distance between vertices in a graph. So, we will start with certain definitions. Initially, we will describe the concepts with examples, and then we will describe the problem and its solution. So, a graph looks like a structure such as this. This is a representation of a graph. It has two parts. So, formally we say a graph is a tuple of two entities. V stands for vertices and E stands for the edges. In this representation, the circles are vertices, which I might label as V1, V2, V3, V4, 5, V6, 7, V8, and V9. So, the elements of V are V1 through V9. The second set is called the set of edges, which is a set of two sets containing two elements in it. So, a typical element in this graph is a subset of two elements V1, V2. So, our E in this case in representation, this subset of two elements is denoted by a line segment running between V1 and V2. So, there are edges like V1, V3, V1, V4, V4, V5, V5, V6 and so on. These are called edges. We denote, typically we denote the set of these two elements in this fashion. Hence, there is no difference between V2, V1 and V1, V2. Okay. We consider them as the same. Let us look at another graph. V1, V2, V3, V4, V5, V6, V7, V8. Let us call this as G1. This is another graph, G2. V1 is on 9 vertices, G1 is on 9 vertices and G2 is on 8 vertices. Number of edges in this graph, the number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think there are 13 edges in this. In this case, there are 4, 5, 6, 7, 8, 9, 10 edges. Okay. Now, I am going to describe some of the concepts related to graphs. A subgraph of a given graph, for example, say I have G1, a subgraph of G1 is another graph where the vertex set of subgraph is a subset of the vertex set of the mother graph G1, and the edge set of the subgraph is also the subset of the edge set of mother graph. So, an example of a subgraph this is a subgraph of G1. The second notion, I will give you actually another example of a graph which is not a subgraph. This is a subgraph, of G1. On the other hand, this one was V3. This is not a subgraph of G1, not a subgraph of G1. The reason being, edge V3, V4 does not belong to G1, hence this is not a subgraph. The next concept is that of a path, walk and a cycle. A path is a sequence of vertices of the graph such that every successive vertex pair has an edge between them. So, in this case, an example of a path is V1, V2, V9, V7. The condition is that no vertex should repeat in the path. This is a path. Now V1, V3, V2, V1, V4 is not a path, simply because V1 is repeated. The concept of walk is when we allow repetition. When we allow repetition of a vertex, of an edge, any number of times, then that becomes a walk. So in our example of G1, okay, V1, V3, V2, V1, V4 is a walk. This is a walk. But V1, V4, V3 is neither a path nor a walk. And that is because there is no edge between V4 and V3. The example of a cycle. A cycle is a sequence of vertices where the first and the last vertex is same and no other vertex is repeated. And again, every successive vertex pair has an edge between them. So here we have V1, V2, V3 is a cycle, and actually I'll write down this way: V1, V2, V3, V1. This forms a cycle. Let's go back and just verify that this V1, V2, V3 is a cycle. Okay. The next concept we want to introduce is the notion of connectedness. Cut. I think I'll have to clean up. Okay. Next, we describe the notion of connectedness. A graph is connected if there is a path between every pair of vertices. In our example, in graph G1, there is a path between every pair of vertices. If you take V1 and V7, we have V1, V3, V8, V7. We in fact have more than one path: V1, V2, V8, V7, V1, V2, V9, V7, and so on. That way, every pair is connected. In the second example, in G2, if you notice, there is no path between V4 and V8. In that case, this graph will be considered to be not connected, as against G1 is connected. So we say that G1 is a connected graph, but G2 is not. So this is the notion of connectedness. Next, tree is a special kind of graph. if a graph is connected but has no cycle in it, such a graph is called a tree. Neither of these two examples constitute a tree. For one thing, both of them have cycles, and in the second case, it's not even connected. So, an example of a tree would look like, perhaps, will look like this. This is a tree. A closely related notion is that of a forest. If we drop the condition of connectedness in the tree, then that becomes a forest. So, any graph without any cycle is called a forest. An example is, this is also an example of a forest, so is this one. Both of these graphs, this as a single graph and this graph, both of them can be considered forests. Next, I am going to describe the notion of a spanning tree. A spanning tree is a tree in context of another graph. So, we say of some graph G. The idea behind this is that this is a subgraph of G, which is a tree and which contains all the vertices of G. The word spanning refers to that. So, an example here, a spanning tree, a spanning tree of G1 could be V4, V1, V3, V2. V6, this is one spanning tree of G1. Notice that it covers all the vertices of G1 and it is a tree and it is a subgraph, which means it does not use any edge which is not present in G1. Now, I am going to state a few observations regarding graphs using only these notions. First observation is that in a tree there exists a unique path between each pair of vertices. If you take a look at this tree, you see that there is exactly one path between every pair. Consider V5, V8, this is V5. So, we have one path V5, V4, V1, V2, V3, V8. That is the only path between V5 and V8. You pick any pair and you notice that there is exactly one path. That is not true in general graphs. For example, between V2 and V3 there are several paths, one of them being just V2, V3, other is V2, V8, V3, a third one V2, V1, V3, a fourth being V2, V1, V4, V8, V3 and so on. Another useful observation is that in a tree T equal to V comma E, the number of vertices is always exactly one more than the number of edges. Take a look at that example again. We have 9 vertices and 1, 2, 3, 4, 5, 6, 7, 8 edges. That is always the case. Okay. Now again we define a few more notions. The one that we want to introduce next is called length. Length of a path or a walk or a cycle. In all the cases, the length refers to the number of edges in that entity. So let us take an example of a path V8, V7, V6, V5. This has got 1, 2, 3 edges in it. So example, in G2 path V8, V7, V6, V3 has length 3. Walk V5, V8, V6, V8, V7. It's certainly a walk. V5, V8, V6, V8, V7. This has length 1, 2, 3, 4. There are 4 edges on it. In case of a cycle, V5, V6, V7, V8 and followed by V5 has length 4, because there are 4 edges on it. Now, related to the notion of length, we describe the notion of distance. Okay. Distance is associated with any pair of vertices in the graph. So, the idea is that given any 2 vertices, the length of the shortest path between the 2 vertices is called the distance of that pair. Here example, delta G1, V1, V7. In G1, consider these 2 vertices V1 and V7. V1 and V7, there are several paths, and one can actually work out carefully and see that there is no path of length less than 3 between them. So, of course, there are several paths of length 3, this one, this one, this one. Then the third one is this, this and this. Other paths are of length greater than 3. So, the distance for this case is 3. Okay. Another example, delta G2 of V1 and V7. This time I am looking at graph G2 and the distance between V1 and V7. In this case, what you notice is that there is no path between V1 and V7. Hence, we describe such distance to be infinite. The shortest is actually no path. There is no way we can reach from V1 to V7. Hence, the distance is infinite. After introducing the notion of distance, the next thing I want to talk about is the shortest path tree. Of a graph G with respect to a vertex S of G. So, you are given a graph, you are given a specific vertex of G, and then we talk about a structure called shortest path tree of G. This is actually a spanning tree of G, which satisfies the following property, namely that a spanning tree T of G such that delta T of Sx is delta T, delta G rather, of Sx for all x. So, let us take an example. Consider the graph G1 and vertex V3. Okay. So, shortest path tree of V3 and the graph is G1. So, consider the following graph V3, V6, V1, V2, V8, V7, V9, 4. Okay. So, this is indeed a spanning tree, we cover all the vertices. We are looking at vertex V3, and in context of V3, if you notice the distances from V3 to each vertex in G1 and in this graph, in this tree T are same. For example, distance between V3 and V4 is 2 here, and the shortest path from V3 to V4 in G1 is also of length 2, and same is true with respect to every single vertex. So, this is an example of a shortest path tree of vertex V3 in graph G1. Now, I am going to introduce one more result, and that is the following. If in a graph G, if in a graph G V1, V2, Vk is a shortest path, then Vi plus j, a subpath, is a shortest path between Vi and Vi plus j. What we are saying is, if this is the shortest path between V1 and Vk, then you pick any segment of it, say from position I to position I plus j, that segment also is the shortest path in the graph between those two respective vertices. And let us get a sense why, because suppose you had a shorter path between these two. So, what you had was a Vi here and Vi plus j here, and you could discover a shorter path than this one, then you can plug in, remove this and plug that path in. Now, what will happen is the length of this structure will be lesser, although this may not be a path. If this is not a path, then there will be cycles in it. You can delete them symbolically. Here is original path, and now I have found, well, from looks it does not look a shorter path, but suppose that this path is shorter than this path. Then you can remove this and you end up getting I have deleted this segment and replaced that by this, which is supposed to be shorter, and I get this path, this structure. Now, this need not be a path, say this is a cycle. Then in that case, we can cut off. If you notice, here is a cycle, this is a cycle, and this is a closed walk. It starts here and ends here. So, I can delete this structure out of the thing and end up getting even shorter structure. If you remove all such closed cycles, you get a path between the same two end vertices, which will be strictly shorter than the original path, but original path was shortest, hence this can't happen, and this better be the shortest path in the two vertices. Okay, so far we have seen all the concepts that we needed for our problem. Now, I am going to introduce the problem. Problem is to compute a shortest path tree for a given vertex of a given graph. Okay. Now, we will introduce the algorithm for this and then see the correctness of that algorithm. But before we go into the algorithm, I will give the definition of two more entities, the two data structures that one uses to describe graphs. So, these are very useful data structures. The first one, so it is data structures for graphs. The first one is called adjacency list. This is an array we may call ADJ, where the argument is a vertex of the graph, and ADJ of a vertex V points to a list of all the vertices with which there is an edge with V. So, this could be a list of U1, U2, where VU1, VU2, etc. are all in the edge set of the graph. We also call such vertices as neighbors of V, or we also call that U1 is adjacent to V, U2 is adjacent to V, and so on. The second data structure we may use is called adjacency matrix. This is a matrix, say A, of size number of vertices times number of vertices. And the way it represents a graph is that A of Vi comma Vj is 1 if Vi comma Vj belongs to the edge set, 0 otherwise. Okay. So, these two data structures we may find useful in describing algorithms. Now, let me come to the main algorithm to solve the problem of computing the shortest path tree. Now, in order to get a sense of the algorithm, we will first see the basic technique behind it. To describe this algorithm, let us recall how light emanates from a source, a point source, say S. A wavefront of this light is the set of points where all the light reaches at the same time, which starts from S at the same time. Further, if we want to compute the next wavefront, then from Huygens principle you pick each of these points and then again form these local wavefronts, and they take their cover, and what you find is this is the next wavefront. The importance of the wavefront is that since it is the set of points where light reaches at the same time, therefore, in a homogeneous medium the distances are same from the source. So, these are all the points which are at the same distance from S. Now, we are going to emulate this process in our algorithm. What we will do is that we will start from vertex X, point S. For our case in the graph, a point will be a vertex, and identify all the vertices which are adjacent to S. See, our graph is a discrete universe. So, we have immediate neighbors, those are going to constitute the first wavefront. After discovering all the vertices of S, then we will pick one of these vertices and find out all the new vertices which are adjacent to that vertex, and we have not yet discovered, we will discover those. And then we will take the next guy and find all the new neighbors we can discover from this, and then we go to the next one and discover the new vertices, and then go to the next one, and so on. After we have done that, we have found the second wavefront, and after completing the second wavefront, we will start with the vertices of the second wavefront, and again repeat this process. Of course, if there are back neighbors, we are not interested in them. We always discover new neighbors, and that is how we form the third wavefront, and so on. This is the idea. Now, in computing this, we are going to use a data structure Q. Where, of course, you know that an element enters into the queue from one end and exits from the other. The advantage of using a queue is the following. While we are trying to discover the neighbors of a vertex, those which are pending and we have yet to discover those vertices will stay in this data structure. We will pick the foremost vertex, the vertex in the front, we will find out all its neighbors. They will form the next wavefront, and all the ones that we have discovered will enter them here. So, if there are vertices in this portion which corresponding to the same wavefront, the vertices of the next wavefront will always be behind it, and you will not start discovering their neighbors until you are done with the neighbors of these vertices, because of the data structure. That justifies the use of Q. So, here we have our algorithm called breadth first search. This algorithm only emulates this process in exploring the space starting from a vertex, and then we will see how we can use it to determine the shortest path tree. So, let us start with the algorithm. The first step is to initialize Q to an empty Q. Now, as you notice that we explore the neighbors of a vertex once, and then this vertex is of no use for us. So, in case we revisit this, we want to make sure that we do not again do the exploration starting from that point, or so called expansion from that point. For that purpose, we are going to use a status. Initially, all the vertices will be set to status unvisited, indicating that we have not visited them yet. There is one more information we are going to store, which we will show later on. Initially, it is all nil. Now, S is our first vertex. We are going to set its status to be current, and what this indicates is that currently I am going to search its neighbors. I am going to put this into the queue. All those from which we have to search the neighbors are going to be set into the queue. and then we begin this loop in which we pick the front element of the queue, namely u, and then for each neighbor of u we do something. We pick all the neighbors and check whether its status is unvisited. If it is not unvisited, then we know that we have already reached it. We are not interested in those vertices. But if v is being visited for the first time, we are going to set its status to current, because we are going to now search the neighbors of this vertex. And now here I am going to tell you what this new parameter is. The parent of v, here we are going to record how we reached v for the first time. We reached v through u. So we are going to set it to parent of v is u. And now this v, which will give me the next set of vertices in the exploration, has to go into Q. So NQ is entering the vertex into Q at the back. Once we have visited all the neighbors of U, we will set its status to visit complete. Visit complete. Now this is of no interest to us. We will complete this. Okay. And then later on I will show you that we are going to get a spanning tree from this, which is actually the shortest path tree of S, and this spanning tree is the following. It constitutes all the vertices of our original graph, and the edges in it are the following: parent of V and V. For every vertex and its parent, such pairs will constitute the edges of this graph, which we will show later on to be a tree. Now, what we have seen here is that we discover the vertices corresponding to one wave front. Once all the vertices are taken care of, then we move to the next wave front and so on. So if I label the vertices with the wave front to which it belongs, then I will actually get the distance of that vertex from S. So what we do is, initially when we are initializing the vertices, we can set the distances of every vertex to be 0. We know the distance, so 3 prime is distance of S. Well, actually that is taken care of. Distance of S is also 0. We do not have to do anything about it. But what we notice here is, as we discover a new vertex from vertex V from U, we are discovering a vertex of the next wave front. Hence, we will set the d of V as 1 plus d of U. So what you learn here is that the d of V is nothing but the wave front to which vertex belongs. Now, in order to prove the correctness of this algorithm, I need to prove certain claims. So I am going to first state them. The first claim that each vertex enters and exits Q exactly once. Now, to see this, observe the following. Recall that our graph is connected. Now, in our graph, if this denotes S and this is any vertex x, then let there be some path because of connectedness denoted by this. Initially we know that S enters the Q right at the start, and when we expand, its neighbors enter the Q. Now suppose up to certain point, let us say this is some y1, y2, y3, y4. So suppose up to some point here vertices have entered the Q some point in time. Then when we expand this vertex, one of the neighbors will be y3. So either y3 was discovered for the first time here, or it was discovered earlier. Either way, y3 must also have entered Q. Hence, this also should have entered Q sometime, and so on. Hence, eventually X must have entered the Q as well. Now, what we see here is the use of the status ensures that every vertex enters exactly once. So we know it enters at least once, but it does not enter again simply because after exiting the Q, we change its status. So it exits from the Q, we do certain processing and then set its status to visit complete, and hence it is not eligible to enter the Q again, because for entering we check whether it is unvisited or not. So it will never enter again. That guarantees that every vertex enters exactly once into the Q and exits, hence exactly once. The second claim that the d values of vertices are non-decreasing in the order of their exiting from the Q. So a vertex that exits earlier has a d value less than or equal to the vertex that exits later. Okay. So we will say that if U exits Q before V, then d of U is less than or equal to d of V. Further, if U and V coexist in Q at any point in time, then d of V minus d of U, which we know is greater than or equal to 0, is not greater than 1. So if they are present simultaneously in the Q, then the d values cannot differ by more than 1. How do we see this one? So what we see is that if this is the Q and this is the direction of the Q, then let's say this is our U and this is V, say the front and the end vertices are U and V. Then when we are going to expand, its children will enter here, and their d value will be the d value of U plus 1. So the next vertices will have d values 1 more than the d value of U. And if we believe the first part, then the d value of U must be between the d value of U and 1 plus d value of U. So that will guarantee the second part. And how do we see that the d values are monotonic, they can never decrease as we proceed, and that is because such a statement is true initially. Initially there is only S in it, its d value is 0. Then its children enter into the, so if I were to show this, initially S and then its children come, say V1, V2 and so on, Vj, their d values are 1, and then of course when one of these is expanded, the d values become 2. So in general, if at up to certain point, the d values of the successive vertices that have entered the Q has only increased, then the last vertex here has highest d value among all. Then the next vertex that will enter here, now its d value is 1 plus d value of some earlier vertex u. This is the d of u plus 1. This vertex has d value greater than this, and hence their children that will enter here will be d value of 1 plus this. If this is say v and this is w, then we have the inequality d of u is less than or equal to d of v, and d of w is d of u plus 1. Hence d of v, the next vertex that comes here, say x plus 1 will be the d value of x, which will be greater than or equal to d value of w. So this will remain monotonic. We will continue this discussion in the next lecture.